there, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today's episode, we're going to be talking about we're going to continue our discussion on equilibrium. So last time we talked about K, we're going to throw another letter at you. How about Q? What the heck is Q? Q is the reaction quotient. So the reaction quotient pretty much tells us the concentrations if we are not at equilibrium. So this is going to tell us either if we are not yet at equilibrium or past equilibrium. And this is how it works. So let's take a look at the example that we looked at last time. Hydrogen plus iodine, we get hydrogen iodide. And let's say that the K value is 49.5. And remember, the K value is only good at a specific temperature. So we have to define the temperature that it's good at. And so here's the equilibrium constant expression. We've got the products on top, reactants at the bottom, and the coefficients as exponents. Okay, so let's say we did two experiments at different times, and we measured the concentration of the two reactants and the one product at two different times. We did experiment 1, we got these values, and we did experiment 2, we got these values. And so if we plug these values for experiment 1 into the equilibrium constant expression, we get 4. And if we plug in the experiment 2 values into the same expression, we get 103. These are the Q values. And what can the Q value tell us? Well, if the Q value is equal to equilibrium constant, the K value, then it tells us, hey, perfect, we're at equilibrium. And we don't need to shift anywhere. If the Q value is less than K, so right here, this Q value is less than K because K is about 50 and Q is at 4. Then we need to say that this reaction needs to move towards the products more before it reaches equilibrium. Right now, there's a lot of reactants. It needs to move towards the product side more before it reaches equilibrium. If Q is greater, like in this case where it's 103 and our K is at 50, then it needs to produce more reactants before it goes into equilibrium. So the Q value will actually tell us in what stage or where we are in relation to the equilibrium point. Okay. Le Chatelier's principle. Le Chatelier, French chemist, okay? And he pretty much said this. If you're at equilibrium and you put some kind of stress on the equilibrium, let's say by changing one of the concentrations, changing the pressure, changing the temperature, or adding a catalyst, if you stress out that equilibrium somehow, the equilibrium is going to move so that it goes back into equilibrium. Okay, you have a stress, it's going to shift and it's going to go back into equilibrium. Okay, now there are 4 things that can happen. We can change the concentration, the pressure, the temperature, or add catalyst. Notice that all of these do not change the K value except for temperature. Temperature is the only one that is actually going to change the K value or the equilibrium constant expression. Okay, and how it changes is according to this. Increasing the temperature causes an increase in the value of K if it's endothermic, if delta H is positive, and it's going to decrease the value if delta H is negative. Okay, so increasing the temperature will cause endothermic reactions to increase, and decrease for exothermic reactions. So let's take a look at an example. So here we have an equation at the top. We've got sulfur dioxide plus oxygen will give us sulfur trioxide. And this is exothermic because we have a negative delta H value. So we want to know which way the equilibrium is going to shift according to these changes. So number 1, if we add a bunch of SO2, so if we add a lot of SO2 here, which way is the equilibrium going to shift to go back to the equilibrium? So if we add a lot of this, then we need to move some of those to the products so that it evens out again. So if we add a bunch of SO2, it's going to shift to the right. So if we add a lot of products, then of course it's going to shift to the left towards the reactants to even it out. Okay? If we remove SO2, so if we make a giant hole right here, the only way to fill in that hole is for SO3 to move towards the reactant side. So that's going to shift to the left. And same thing if we make a hole at the SO3, there's a giant hole right here. If we remove SO3, it's going to shift to the right to fill in that hole. Now for pressure, the way you do pressure is you have to look at the number of moles of gas. So on the left side, we've got 3 moles of gas, and on the right side, we have 2 moles of gas. So if we increase the pressure, if we start to squeeze this container, the 3 moles of gas are going to feel more pressure than the 2 moles of gas. And so they're going to want to move towards the product side, okay? So if I increase the pressure, the side with more moles of gas is going to move in the opposite direction. So we have 3 moles of gas here, so it's going to want to move towards the 2 moles of gas side. Let's move to the right. If we decrease the pressure, then the side with more moles of gas is going to move towards that side. And so it's going to move to the left. Now, for these temperature ones, delta H is negative, which means it's going to make this reaction hotter, okay? So if we increase the temperature, we do not want the temperature to get hotter. It's actually going to get colder in response to that increase in temperature. Remember, it's going to shift according to the equilibrium. So if this is releasing heat, we don't want it to go towards the products because that's going to make it even hotter and hotter and hotter. We want to counteract the increase in temperature. So we're actually going to move to the left for this one. If we decrease the temperature, if we were to make it colder, then now we want it to get hotter. And so we're going to move towards our product side. It's going to move towards the right. And lastly, if we add a catalyst, there's no change, no shift in equilibrium. It's going to happen faster. It's going to occur quicker, but there's going to be total, overall, no change.